Let's take a look now at the bit shift operators. Right, the right shift and the left shift. So the right shift looks like two greater than signs, no space in between. The operands may be of any integer type, both signed and unsigned. They can be chars, shorts, ints, longs. All right, we're going to commonly work with the unsigned, so we won't worry about the signed. But we want to know a right shift is going to shift the rightmost bits off the right end, and it's going to replace then the missing bits with 0 bits on the left side. So it's going to shift them off the right, put zeros on the left, right, for unsigned numbers. The effect on signed numbers is implementation defined, and most everything we want to work with is going to be an unsigned bit. It's going to be something that's usually in a status register, right? So that's what we'll be working with in all of our examples. Right, so let's take a look at what happens if we right shift. So if we have the hex number 0xFF, remember this is a hexadecimal constant, and if we say right shift that by 1, so what we have on this side of the right shift operation is the number of bits to shift to the right. So here's then the binary representation of hex FF, which is all ones, an 8-bit number. Right, shift 1 means shift all bits to the right and add 1 0 on the left. So when we take hex FF shifted by 1, it's this binary string shifted by 1, which gives us the result. It's going to remove, think of this rightmost bit as coming off the right end, and we're going to replace it on the left side then with a 0. So we're just shifting everything to the right, replacing with zeros on the left, and that hexadecimal representation of that result is 0x or hex 7f. Right. If we use the same constant, hex FF, and we shift that to the right by 2 bits, right? We're going to shift all bits to the right and add 2 zeros on the left. So we're going to lose the 2 rightmost zeros and then add 2 zeros on the left. So shifting that 2 gives us this result of 0 0 1 1 1 1 1 1, which is hex 3F. Right? Similarly, if we take hex 3FF, shift it by 3 bits, we're going to shift 3 bits to the right, we're going to add 3 zeros on the left. So here's the 3 zeros we add on the left. This gives us a hex 1F as our final representation. And now let's take a look at how we do this with variables. We were doing it with constants, so we're going to create 3 variables here. All of unsigned char. So this one's named value, and I'm storing hex FF in it. This one is named shift amount. I'm storing a 1 in it. And then we're going to use result to store the results of our shift. So if we take value, which is hex FF, shift it by shift amount, which is 1, well, we've seen then that gives us the result. We're going to shift 1 off the right and put 1 0 on the left. That is going to give us a hex 7F, right? We're going to store that in result. So let's go ahead and take a look at example 4. Yeah, let's pop up code blocks here. Right, so this illustrates the result of a right shift operator. So here is our variable name value. We're assigning hex FF to it. We've got result here, and what I've written in is a for loop. So shift amount is declared here. We're going to start that at 0, and as long as shift amount's less than 8, we'll run through this loop. So we just take what's stored in value, which is hex FF, and we're going to right shift that then by shift amount. So when we shift that 0, we'll see this doesn't change. We're just going to print out those results. So let's run this. And let's take a look at the results of going through the loop. So hex FF, right shifted by 0 gives us the same. Hex FF, right shifted by 1 gives us 7F. Hex FF, right shifted by 2 gives us 3F, and so on. So you can see then the results of this are that we keep shifting so this number of bits off the right and 0 filling on the left with the same number of bits. More effectively, when we right shift, we're reducing this, right? We can see that these numbers are getting smaller and smaller. And so this is just a simple way to use a for loop to vary the shift amount. Notice then what we store in value doesn't change at all, right? When we say value right shift by the shift amount, we're storing that result. So value is not changing then in memory. It has this constant hex FF in it because we're not changing that. And let's take a look then at the left shift. Right? So the left shift, right, just works in the opposite direction. It looks like 2 less than signs. Once again, the operations can be of any integer data type, both signed and unsigned. We're going to shift the leftmost bits off the left and replace those with 0 bits on the right. Let's take a look then. We're going to use our hex FF. We're going to left shift 1 bit. So there's our binary representation. And if we shift to the left, we're going to shift all the bits over to the left, and we're going to add 1 0 on the right. So we take all of these bits, we shift them over to the left, and we add the 1 0 on the right. And we still have that same 8-bit representation, but now that is hex FE. Similarly, if we take hex FF and shift by 2 bits, right, we're going to shift all the bits to the left, and we're going to add 2 0s on the right. So we're going to shift all of these ones to the left, add our 2 0s on the right, and we're going to get a hex FC. Doing the same thing with variables, right? We declare then this variable value, shift amount, result, and we're going to run that and see that in example 5. Let's go straight to example 5 then. Here. Let's add this into our project. And remove example 4. And let's build and run here. All right. So what this does, right, value has then, we've stored hex FF. Result then is a variable that we're using to store the result of these operations. Same for loop. Shift amount set equal to 0. Right, it's going to increment by 1 each time we go through here, and you can see that hex FF left shifted 0 bits, still gives us hex FF. Hex FF shifted 1 bit, gives us FE. Shifted 2 bits gives us FC, right? 3 bits, F8. So all we're doing is the shift amount is the number of bits then that we're 0 filling on the right. Right? And you can see these numbers then, right, are changing. If you write out the binary patterns, you'll what? See the bit value shifting. Left shift, we shift to the left, put 0s on the right. Right shift, we shift to the right, we 0 fill on the left. And so that's how the shift operators work. In our next segment, we'll go ahead and take a look at how many bits, how we find out how many bits are in our data. And we might as well do that right here, right now. Well, this video is somewhat short. So we want to read individual bits, that's our goal. And we need to know how many bits we use to represent things. So there's actually a macro called char_bit. And the reason we want to query this is the number of bits in a bytes depends on our particular system, that system's architecture, and then possibly library implementations. But one thing that is consistent is that the size of a char is always a byte. And to find out how many number of bits in a byte, we're going to query this macro constant char bit. It's defined in the header file limits.h. So let's go ahead and pop open example 6 here in code blocks. So let's open 6, 7. All right. So to find out how many bits in a byte, right, I've included limits.h because that's where char_bits defined. And we're just going to, let's run this. All right. So we see our output says there are 8 bits in a char byte. So there are %u. So here, char bit will be substituted in for %u. That's where the 8's coming from. And we'll see that there are 8 bits then in a char, right? And a char is commonly a byte in any system. All right, so we can depend on the char being a byte. We can use char bit to tell us how many bits are in a byte then in our program. And we want to revisit then the sizeof operator, right? The sizeof operator is going to return the size in bytes of a variable or a data type. Right? And I've got a couple examples here as well, right? If you run example 7, you're going to see now that char bit, but we use char bit to tell us how many bits in a byte. But we're going to now print out the size of a char. I left that little comment in. We'll see then that when we run this, there are 1 byte, and that's bad grammar, there are 1 bytes in the char. So size of char returns 1, number of bytes. And then if you want to know how many bytes are on different data types, here in example 8, right? This will print out then. So how many bits are in these data types? We're going to take char bit, we're going to multiply that by the size of a char, and then char bit times the size of a short and size of an int. And so you can see now that we're going to have 8 bits in a char, 16 bits in a short, 32 bits in an int on the system that I ran this in, right? So there's 1 byte in a char, right? So 8 times 1. There's 2 bytes in a short, so 8 times 2 is 16. This returned 4 bytes for size of an int. So 4 times 32 gives us the number of bits. So we can actually, in our C program, use this if we need to determine as the program's running how many bits there are in an actual data type, depending on our library implementation system architecture. We can do the same thing with identifiers. Here, right, I queried then size of char, size of short. And you've got these examples that you can run and experiment. Here in example 9, I changed that then. I made 3 variables or 3 identifiers, C values of type char, S values of type short, and I values of type int. So you don't always have to query the data type, you can query the identifier name. So we get the same result, char bit times size of C val. Well, C val is the identifier name, but because C val is a char, we're going to get 8 bits in the char C val, right? Because S val happens to be of type short, we'll see that there's 16 bits in the short. And then since I val is of type int, we'll see that there's 32 bits of type int. So the difference here was that I used size of with the identifier names. Up here in the previous example, we used size of with the data types. But this always knows what data type this is, and it'll tell you then how many bytes associated with that. All right, in our next video segment then, we'll learn what bit masking means, how to create bit mask, and how to read and write those bit values.